In this video we're going to look at the OCR Advanced Information for Foundation Combined Science. Now this does also come up on the triple physics paper, but it also includes magnets. I don't really know what they're going to do with magnets, so I'm really going to focus just on investigating forces and springs. And if you are studying triple science, then I would probably recommend you also think about balanced forces and find some revision materials for that. So the classic investigation is to see how the force on a spring affects its extension. So let's look at a method for that. Well, the very first thing we need to do is to measure the original length of the spring. So that is the length of the spring with no masses on it. We then add 1 newtons, which is equivalent to 100 grams. Newtons is force, grams is mass. We measure the new length. We repeat until we've added a sufficient number. It might be 5 newtons, it might be 6, it might be 10 newtons, which is why I've just put approximately 7 newtons. 7's usually a good number. And what's really important is the extension is the new length minus the original length. So this here, if we read off here, 5 is not the extension. We need to subtract the original length, which is going to be a shorter length. Now sometimes they might ask you, how do you convert from mass to weight, which is a force? Well, we can do that by saying weight equals mass times the gravitational field strength, which is an equation that is on your formula sheet and one that is really important to remember that is there. So weight is a force in newtons, mass is or should be in kilograms, and gravitational field strength is 10 newtons per kilogram. So for every kilogram you have, gravity pulls with a force of 10 newtons. So here 100 grams is 0.1 kilograms, and we have 1/10 of a kilogram, so when we multiply by 10 we're going to have 1 newton. Now sometimes they will ask you to do this, sometimes they might not, and they might just give you force straight away. Okay, what can you do to make this a better practical? Can you do to get better results? So what we need to do is use something like a pointer. So we need to attach a pointer on to the end of the spring that points directly to the ruler. And the reason we do that is to reduce an error that we call a parallax error. So what does that mean? Well, if I do not have this pointer and I look at it, if I'm looking at it from slightly above, when I look at what I think is the bottom of the spring, I'm going to get a value that is very, very different to the true value. And if I was to look at it from below the level of the spring, I will get a value that is different to what I should be measuring. Now you might say, well, hang on, I'm never going to be that silly. But even if you are a little bit off, even if your eye was only a tiny bit above where it should be, you will get a different value, and it could be quite a large difference. So we attach a pointer, and here is a photo of some equipment. So sometimes they might give you a photo rather than a diagram, and you can clearly see here we have this pointer is highlighted on it. The other important thing that we must do to make sure we get a good set of data is we must make sure this angle here is 90 degrees, is a right angle. So we can obviously use a protractor or a set square to make that angle 90 degrees. So you could also add on at the bottom of your method, use a pointer to reduce parallax error, and use a protractor or set square to ensure the ruler is at 90 degrees. Okay, so that should be enough to explain how to do the method. So let's look at a couple of exam questions. So this first one here, it tells you that a student measures the extension of a spring when it's stretched. Now they've been quite nice here, they've given you newtons. Now they have given you centimetres. Usually we want things in metres. But the graph is in centimetres, so for now we don't need to do anything. Now I've plotted the graph for you. Obviously you can't do this on a screen. But what I wanted to show you is really easy to make mistakes. I made some really silly mistakes. So always double check all of your points straight after you've done them, and then at the end of the paper, because it's so easy to make mistakes. Now I'm just going to give you a quick tip for drawing lines of best fit. Right, a lot of people will just plonk the ruler on and draw a line of best fit. That's not a sensible method, because you will get it often in the wrong place. So if you put the ruler on its side like this, you can adjust it so that half the points are either side. So it might be that it's too low and all the points are above it, or it's too high and all the points are below it. So you can adjust it and you can see nice and easy where it should be before we draw our line of best fit. So what I'm going to do, I'm going to leave the graph here and 3 short questions for you to complete now. So pause the video and try these questions. So part B, it says use the results and the graph to show the spring constant is 35 newtons per metre. So I already highlighted this as in centimetres. That's a very common trick. So we need to make sure we convert to metres at some point. We also need to know what the spring constant is. So when we look, spelled that wrong, constant. The spring constant is the force needed to extend the spring by 1 metre. If you remember that, it's really easy to work this out, or you might have looked up on the formula sheet and written down that force is spring constant times extension. So if you did this method here, let's think, well, what's the extension? I'm going to use a nice big triangle on my graph. So I'm going to draw a nice big triangle here, and I can see that my extension is 0.2 meters, right? Because 20 centimeters equals 0.2 meters, right? We are dividing by 100. The force needed for that is 7 newtons. And my spring constant is what I'm trying to work out. So I just write it here to be meter. 7 is my spring constant times by my extension. So my spring constant is 7 divided by 0.2. So then I can put that in my calculator and I can get my answer, which is 35 newtons per meter. Okay, if you don't get the answer that it says, you've probably made a mistake, which might be you haven't converted to meters. Part B, calculate the energy transferred to this spring. So again, we look up on our formula sheets the equation, we write it down exactly how we find it. So it's a half times the spring constant times the extension squared. Now, the most common mistake is people miss out that it's the extension squared. So the energy stored is half times 35 times by 0.2 squared. So we must write that in, we must type that in our calculator. The amount of people that miss that out is quite worrying. So 0.2 squared, and that gives us 0.7 joules. And then finally, what's the minimum number of forces that are acting on a compressed spring? So the spring, it would normally be like this, but it's been shortened like this, where you obviously need a force to compress it at one end, but if it was just that one force, the whole spring would move this way. So there must be another force acting in the other direction, which means the answer is B, which is 2.